I'm going to finish up section 11.1 now, and so in the last video we were looking at systems of equations where there were mostly it was just two equations with two unknowns. Here I wanted to show you a couple of 3x3s, and then I thought we'd do a couple of problems in the book. So in this example I want to solve this 3x3 system, and now usually when we have a 3x3 or bigger system, the plan is going to be, at the moment at least, to use the elimination method repeatedly in order to begin. So in this problem here, I'm gonna eliminate x. If I use the first and second equations, eliminate x, I'd want to multiply the top equation by -3 and then add those. If I use the first and third equations and eliminate x, then I'd want to multiply the top equation by -4. Okay, so I've got my work done with that. I'm eliminating x here, like I said, on both of these. So here's the first and second equations when I add them together, and then here's the first and third equations when I add them together. In doing that, I have now created a 2x2 system, so it becomes like what we were just doing before. I'm sticking with the elimination method still, although I guess it wouldn't be a huge problem if you were to use the substitution method. And so if we eliminate y now, multiply the top equation by 5 and the bottom equation by -7, and then add. -35y plus 35y is 0, y is eliminated, and it looks like we end up getting 132z equals 132, so z is 1. Knowing that z is 1, we can then backtrack here. So if z is 1, then I can, let's see, add 10 and divide by -7, and so it looks like y would be -2. Knowing that z is 1 and y is -2, I can use any one of these initial equations here. I just used the first one, I guess, and I can get x. So y is -2, z is 1. It looks like x would be 4. X is 6. So I think x is 6, y is -2, and z is 1. If I were to check that, let's see here. 6 minus 4 is 2, plus 4 is 6. That looks good. In the second equation, we are looking at 18, plus 2 is 20, plus 2 is 22. That looks good. And then in the last equation, 24 minus 6 is 18, minus 8 is 8. That looks good. Okay. Here's another equation system. 3x3, same deal. I'm going to start with the elimination method. Again, I'm eliminating x. So with the first and second equations, I'm going to multiply the top equation by 2 and then add. I've done that. And then with the first and third equations, if I multiply the top equation by -3 and then add, then that reduces this down to a 2x2 system. Okay. I guess I've used substitution now, and so if I solve this top equation for z, y would be equal to z minus 9, and I'm going to substitute that into the bottom equation in order to get z. Looks like z is 5, and knowing that z is 5 means that okay, subtract 5 and then multiply by -1, y would be -4 then. And if z is 5 and y is -4, and you plug that into the first equation, there's fine. I'm getting x equal 1/2 then. So x is 1/2, y is -4, and z is 5 would be the solution to that one. Okay, here's another one. Let's eliminate x. So if we work with the second and first equations and then the second and third equations, with the second and the first one, I'd want to multiply the bottom equation here by -5, I've got, and then add those. With the second and third equations, I'd want to multiply the second one by -4 and then add. So okay, I've done that. I'm getting -7y plus 11z equal 15, and then I get another -7y plus 11z equal 15. Well, if I multiply the bottom equation by -1 and then add, I get 0 equals 0. Okay, so this would be a dependent system since I get 0 equals 0 and the variable was eliminated. All the variables were eliminated. And remember that a dependent system means that there are infinitely many solutions. When I give my answer here, I'm giving it as an ordered triplet, x, y, and z. It's just I want everything to be in terms of x or in terms of y or in terms of z. I've got everything in terms of z here. So to get y in terms of z, I would just solve this equation here for y. Y is equal to 7/11 z minus 15/7, and so that's going to go in the y coordinate. To get the x coordinate, we can use the top equation and replace y with what we know in terms of z. I've done that here, and solve this equation for x. So if I solve for x, I'm looking at x equals 3/7 z plus 1/7, and I've got that written now in the x coordinate, so now everything is in terms of z. And this would be one way to describe to somebody how there's infinitely many solutions. You know, if there's any value z that you give me, I'll be able to find x and y values producing infinitely many points that would be solutions to this system here. Okay, we'll look at another option for solving a system in the next section. The last thing I wanted to do here is just kind of take a look at some application problems. I got there's 3 problems in the book that I thought were good to look at. So let's see here. This is on page 736. Problem 60 I thought was one to try out together here. It says that a movie theater charges $9 for adults and $7 for seniors. On a day when 325 people paid for admission, the total receipts were $2,495. How many who paid were adults and how many who paid were seniors? Okay, the idea here is to set up a system that represents the situation and then solve the system. One equation would be representing the number of tickets that were sold. If I let x be the number of adults and then y equal the number of seniors, the number of adults plus the number of seniors were 325 total people. That's the number of tickets that were sold, they told us. Another equation here could be the cost equation. Okay, now it costs $9 for an adult and $7 for a senior. So I've got the total cost of all the adults plus the total cost of all the seniors, going to give me a total cost of $2,495. That's what they told us in the problem. Okay, so here'd be the system representing the problem that we're trying to solve. You can use whatever method you want, I guess, if they're not telling you. I'm using the substitution method here, and so I'm going to solve the top equation for y. And where I see y in the bottom equation, I'm going to replace that then, so that way everything is in terms of x. Solve this equation for x, and you get 110. X is the number of adults, so there's 110 adults that were at the theater. And if x is 110, y would be 215 seniors then. Okay. Problem 68 would be another problem that I had here, and it says that a group of people purchased 10 hot dogs and 5 soft drinks at a cost of $35. A second group bought 7 hot dogs and 4 soft drinks at a cost of $25.25. What is the cost of a single hot dog and what is the cost of a single soft drink? Okay, now in these problems, obviously you want to identify what is x and what is y. Okay, so x is the cost of a hot dog and y is the cost of a soft drink. I've got these 2 groups being described here, so I'm going to have 2 equations, one representing each group. In the first group, they had 10 hot dogs and 5 soft drinks were purchased. So 10 hot dogs at a cost of X dollars per hot dog, plus five soft drinks at a cost of Y dollars per soft drink would give me $35 total then that first group would have paid. Another group bought 7 hot dogs and 4 soft drinks. 7 hot dogs at X dollars per hot dog plus 4 soft drinks at Y dollars per soft drink gave group 2 a total of $25.25. So then I would solve the system, and in this problem I'm using the elimination method, it looks like. Eliminating, let's see, what am I eliminating here? It's going to be Y is what I'm eliminating. So to eliminate Y, multiplying the top equation by 4 and the bottom equation by -5. That way when I add 20y minus 20y is 0. 40x minus 35x is 5x. And then on the right I've got 13.75. Divide by 5 and it looks like x is $2.75. That would be the cost of a single hot dog. And that sounds like a reasonable dollar amount. Okay. Knowing that x is $2.75, we can then get y by plugging that number into the top equation here and solving for y. I'm getting y equals $1.50 then. And of course these sound like normal prices, you know, for whatever this event is going on. Alright, problem 70 is the last problem that I had in my notes. And so in problem 70, it says that Pamela requires 3 hours to swim 15 miles downstream on the Illinois River. The return upstream takes 5 hours. Find Pamela's average speed in still water. How fast is the current? Okay, and assume that Pamela's speed is the same in each direction. So, okay, in this problem, we're going to use the formula distance equal rate times time. And I'm going to be using that twice. So the distance is 15 miles, whether she's swimming upstream or downstream. She swam 15 miles each way there. And so I've got one equation representing the upstream situation, and then another one representing the downstream situation. She's let's see here. It took 3 hours to swim 15 miles downstream. Of course, the current is helping her. So I'm going to let x represent Pamela's speed in still water, and then y represent the speed of the current. Of course, the current is helping her, and so if you add in the current, she's going to take a shorter amount of time for her to swim 15 miles. But then upstream, she's fighting the current. Okay. So it took 5 hours to swim upstream. Since she is fighting the current, I'm subtracting y, that is the speed of the current there. If you solve then this system, I distribute here, and you can divide by 3 and divide by 5 actually. If we use the elimination method, we can immediately eliminate y. 2x equal 8 means that x is 4. If x is 4, we get y to be 1 when we plug that number back into either one of these two equations here. And so it looks like Pamela's speed in still water is 4 miles per hour. That sounds like a reasonable number. And the speed of the current would be 1 mile per hour in this problem. Okay. So that's all I had in this section here. Here's the problems that I'd like you to look at in section 11.1. And we are now done with section 11.1.